Hello everyone and welcome to another VEX tutorial. This one is on Celtic knot fills. The Celtic knot fill was written to fulfill a need that I had to engrave some laser engravings. And it searches for a type of Celtic knot to fill a shape that you've defined and to do it in such a way that it has a more human look than the typical computer look that you'll get from a normal Celtic knot. Okay, to use Celtic knots, you have to use it something like pocketing. You need an overriding shape first. You can have shapes inside for islands and such, but let's test it out with just the shape. First of all, you need to be a group. It only works on groups, and you should only do one group at a time. So let's do a group of that, and we'll just hit the preview button. Now this is your basic Celtic knot. You can see it's a little unusual, and it's a little bit asymmetrical. However, in my intended use, I would copy that or mirror it up, and I would have a symmetrical set as opposed to a single symmetrical Celtic knot. Now you can influence this sense of symmetry in it with this symmetry offset slider. Let's slide it to 0 and see what we get. We get a duplicate of this, and let's slide it up to 99% and see what we get. And you can see at 99% we tend to approach a more mathematical rigidity, and it looks like you'd expect from a gridded Celtic knot. Although there is a little bit of aberrance that looks human as opposed to rigid. So by using the symmetry offset slider, you can play around with, I call it artistic temperament internally, just to slightly change the way the system looks at symmetries. Next, we have the Celtic refinement, and here it'll tell you the number of chords in this particular design. In this case, we only have one chord. You can pick a profile type. It could be a thick ribbon, it can be a thin, flat ribbon. We have ball races, and which is kind of like a roller coaster. They're cupped so that a ball could run in them. You even have a rotating notch, so there's actually a little slice in this tube that rotates around the tube as it goes. In addition to that, let's go back to a round pipe so that we're not looking at anything too strange. We have a modulation and amplitude adjustment so that you can set up a modulation frequency and an amplitude. Nothing happens until we put a modulation amplitude. And what this does is it modulates the width of the chord as it runs around the object. If you go up to extremes, you're actually thinning out quite a bit as it goes around, but this makes it look very humanish, as if a computer was less involved. And it's the kind of thing that I was aiming for when I was designing this. I wanted something that made it look as if I did the chord, as opposed to a computer just designing a gridded result for me. You can get some awfully strange shapes and results from this. The program does tend to remember your settings here in terms of types. So if you find things looking strange, set your first chord to anything you wish that looks normal to you and hit copy to all, and that will allow things to look more normal to you. It kind of resets a reset for what you're doing. Let's look at one, let's go up in density a little. That was a 3 density. Here we have a 5 density. And you can see for whatever reason the program has decided to try to create some strange symmetries at the tops. We get a bilateral symmetry to this, but there is no quadrilateral symmetry. The bottom is quite mathematical. Let's move that up to 99 and see if there's any difference. And there is. It gets more regularized at the top here. This is very much a box of chocolates algorithm. You don't know what you're going to get until you bite into the chocolate. And it's meant to be used to have some fun with, to find a design that you particularly like and you want to machine or burn. There are different types of chords I think I've gone over. You can also set asymmetrical sigmoids. The sigmoid is what joins a tube to another tube as it runs through. And if you have an amplitude modulation on it, an asymmetrical sigmoid will create a shape kind of like this one down here that we can see in this corner. Incidentally, if you hit the control key, you can pan a design. Control and shift will rotate it. You can use your mouse wheel to zoom in. Double click will take you back to normal, and shift control will rotate you over so that you can get a good look at what you're going to get as a result. The photographs that were shown as this video started is the type of output that I use for my laser. Just hit OK when if you wish to have this design. If for some reason you just want chords to show you for some other machining process, you can just select an output of the chords. It doesn't give you any idea of which chord is over or under another one, but they are one line, one continuous line in this case. Now, whether you would have a continuous line or not would simply just depend on how many chords you have. So let's do something different. Let's take a circle and let's move it up maybe into the middle. And maybe we'll take another box and clip that in like that. Oop. My bad, I erased it as I did it. Okay, so now I'm going to take some scissors and join these into a single entity. And then I'll group them into a group. And let's try a Celtic knot on them and see what we get. As you can see, you can get some awfully strange shapes. This one looks almost like it was grown as opposed to designed. Again, your symmetry control will control just how mathematically robust you are in the way things do. Now, here you can see I have two different widths of chords. The red chord is the one currently selected, so we'll go to this chord and we'll thin it out a little bit so that it's kind of even with the rest of them. Sometimes you can turn off a chord and you'll find that that helps your design. In this case, it does not. So we can just uncheck remove chord and we'll be back to where we were. So by adjusting symmetry offset and your density, you can find various types of chords that might fit your needs for that particular shape. You can get some awfully strange ones going up. If you get too high in density, you're going to create massively large STLs, which might be harder for you to control or to machine or manage. But if you find it locking up because it's doing such a complex calculation, there's a stop calculations box here. It's multi-threaded, the area that does the calculations. What could take you the most time is when you hit OK and it has to design that chord and put it on the screen. As you can see here, all I got was my chord here because it remembered the selection that I just wanted, the graphic. The graphic itself can be quite nice as a laser burned object as well, which is why I included it. So let's go back to our Celtic knot and redo that one. Again, here we have a chord that seems to be too wide for this design, and we have 4 chords. So we'll find the thick chords. There's a thick one, and we'll just adjust that chord width down a little bit. And that's a pretty ugly chord, but in the odd event we were going to use it, we'd select STL, and then OK. And there's our chord. Sometimes it can take up to 4 minutes to generate a chord. This one's fairly complex, and yet it generated it quite quickly. So the next thing we should talk about is grayscale outputs. The reason it was written in the first place is so I could do some laser engraving with height maps. And what I'll say from here on is true for all STLs. You can load an STL of a head and do the same type of transparency output that I'm going to do here. So you select a group with an STL in it and hit for a grayscale output. Give it an image name. And it will select, or it will save a height map of that. And here's the image that we got from that particular run. Now, if this had been an STL of a head and you wanted a height map image from it, you can zoom in on an area of an image. I'll show you how to do that. We just simply create another contour. And then we drag that contour over the area of the image that we wish to get a zoomed in version of. Select them both. And then ask for a height map output. And it will zoom in on that particular area. Height map 2. And there it was. And here's what we get as a result when we zoom in on that small area. Anyway, that's it for Celtic knots. I leave it up to you to see if you can find a use for them and have fun.